Swayam Prabha. Digital India. Educated India.
Good afternoon. Anyway, good that at least a few have turned up, otherwise I would have to reschedule the entire class. Anyway, so as one more small correction to the previous class that I just want to bring forward. I think there's one person who observed it and he was correct. The mean temperature for the high speed flows, I had told that it should be 0.5 T wall minus T infinity plus C into, I think it should just reverse the sign, it should be T adiabatic wall minus T wall, where C equal to 0.22. So I think I had given this as C into T wall minus T adiabatic. Someone has correctly pointed out that since the adiabatic wall temperature is greater than the wall temperature, so this has to be positive, so that the mean temperature now is increasing rather than, it should not decrease, because now with the use of adiabatic profiles, for example, if you had plotted y versus t, which we had done, this is your T infinity. From here the profile should start something like this, and so this is your T wall. If you had applied an isothermal boundary condition without viscous dissipation, it would have come something like this. Okay, so therefore you see the average temperature has to now go up. Okay, earlier the average temperature was between T wall and T infinity. Okay, now the actual temperature will be like this, something like it will go up inside. So therefore the average temperature has to account for this increase in the, so therefore this has to be positive here. If this was T wall minus, so generally your adiabatic wall temperature will be greater than your wall temperature. Okay, so this will be positive, and therefore this will increase your T mean temperature, otherwise it will decrease the T mean temperature, which is not physically correct. Okay, so this please incorporate this particular correction, and now we will start a new topic. It is the same solution to external boundary layer flows, but we will use what is called as an approximate method of solution. Okay, so far we have been doing exact solutions, so called exact solutions, where we had derived the similarity equations for the different configurations, and we had solved it, but we cannot solve it exactly, we have to solve it using some numerical method, but nevertheless the solution is for an equation which is actually an exact equation. Okay, now we will look at techniques where we will approximate the solution by means of some profiles, rather than trying to solve by a numerical technique, that the way that we were doing till now. So we don't know the profiles how they look, so but we got that as a solution of the similarity equation. Now we will approximate the profiles as something depending on the order of accuracy. You know, you can use a linear profile or quadratic or cubic or fourth order, whatever polynomial. So we will substitute that into the governing equation. Once you know the profiles, we can determine the expression for boundary layer thickness, the thermal boundary layer thickness, and therefore the heat flux, Nusselt number, and so on. So this kind of technique is also called the integral method. Many people also refer this as the approximate . Okay, so the starting point of this is to start with essentially an integral form of, why this is called an integral method is you operate with the integral form of the governing equation, form of boundary layer momentum and energy. Okay, so why do we use the integral form is of course the integral form is more helpful when you are approximating some solution, putting it inside and integrating it out directly. Okay, so therefore this is more convenient for the approximate solution to work with an integral form, and I am not going to now derive the integral form, because if I remember correctly I had already derived a particular version of the integral form. If you may recollect your earlier notes for the flat plate Blassius solution, we try to find the expression for boundary layer thickness delta, so as something like square root of nu x by u infinity, right. So this was derived by integrating the momentum equation from 0 to delta, and from there we had solved an ODE to get the expression for delta. Okay, so in fact at that time I told that I am not going to derive it again, because we will be using that as a starting point. So the point where we left off, so we integrated the x momentum equations. I am just going to write it just to show you how it looked. Sorry, this is du by dy is equal to nu du by dy between the limits equal to 0 and y equal to delta. Okay, so we just integrate the boundary layer momentum equation for a flat plate. Okay, we could also include your pressure gradient term, so that will be additionally plus u infinity du infinity by dx, and integrated between 0 to y dy, it is nothing but delta. Okay, so how we got this, because originally this term was nothing but minus 1 by rho dp by dx, and we saw in the boundary layer that the pressure gradient along y is negligible, therefore we can apply this equation to the inviscid potential flow outside, and we can directly find that this is equal to u infinity du infinity by dx. Okay, and when you integrate it across the boundary layer, so that will be, this will be constant, okay, for a particular y location, so you can directly say that is multiplied by delta. Okay, so if you have a pressure gradient, that term also enters into this final expression, and after we broke this term, we integrated by parts, and then we used the continuity equation to make some approximations, and finally we arrived at this particular form 0 to delta u du by dx, especially the left hand side, minus u infinity 0 to delta du by dx dy. This is equal to nu du dy 0 to delta plus u infinity du infinity by dx. Okay, so I think we arrived at this particular form for the entire left hand side term after we used the continuity and we integrated it out, and from here we are going to start now. Okay, so this is nothing but the momentum integral equation, but still not the final form. Okay, so I am just going to rearrange some of the terms. In fact, what I am going to do here is I can once again integrate by parts. Okay, so I can do this as d of u infinity u by dx minus u into du infinity by dx. I can just re-express that way, and I am going to multiply throughout by a negative sign, and if I just rewrite this a little bit, so this will be d by dx 0 to infinity 0 to delta u infinity minus u into u dy. So u infinity into u is basically this term minus, this can be neatly written as directly 0 to delta d into uu by dx dy, right. So du square is nothing but 2u du dx, okay. So I can just write this as d by dx, so I can take d by dx out, so 0 to delta, so I am multiplying throughout by negative sign, okay. So I can write this as so this is already negative, negative of negative is becoming positive, so u infinity into u minus uu, okay. So that is this particular term, okay, plus the other term which I have written, this is du infinity by dx, which I can take common from here as well as from the right hand side term, okay. So this can be written as du infinity by dx integral 0 to delta, okay. So here I have a negative sign here and I multiply it with a negative sign, so this should become positive, okay. So this should be a positive, again I multiply it with a negative, so that should become negative, and this one is already negative, goes to the left hand side term, that becomes positive, so this becomes u infinity minus u dy, okay. On the right hand side, now if I integrate this from 0 to delta, so at this at y equal to delta, du by dy should vanish, okay. So this becomes minus nu du by dy with a minus sign, so this becomes positive, this becomes nu du by dy at y equal to 0, okay. So I have probably skipped a couple of steps, but I think you can understand straight away how that comes out. You want me to explain again, or is it okay? Okay, so till here you know how it has come out, okay, from the previous derivation. So from here I am just rewriting this first term as duu by dx, and this I am integrating by parts again, okay. So I can write this as u infinity u d by dx minus u du infinity by dx. So therefore, so this term and this term can be combined, I can take d by dx out of the integral, so 0 to delta u infinity minus uu, okay. So this is u infinity into u, this is uu, so I take small u common, u infinity minus u dy, and the other two terms, so here du infinity by dx is common to this and this, okay. So and I can write this as, instead of writing this as delta, I can write this as 0 to delta dy, okay. So that is u infinity, that is basically this u infinity into dy minus, there is again this u dy, okay. So which is what I am writing here together. On the right hand side term, this is 0 to delta, so at delta du by dy is 0, right. So therefore this is minus du by dy at y equal to 0, already multiplying throughout by minus, so this becomes nu du by dy at y equal to 0, okay. So this is my final expression. In fact, I can also rewrite in a more familiar form, so I can write this as d by dx of, I can take multiply and divide by u infinity square for this particular term, so this will be u infinity square into, I will just denote this as something like delta 2 plus in this case I can multiply and divide by u infinity, okay. So I will call that as some delta 1 into du infinity by dx, on the right hand side I have this as it is. So where my delta 1 will be, so multiply and divide by u infinity, so this will be u infinity 0 to delta, so this is u infinity by u infinity which is 1 minus u by u infinity, into dV. Okay. So okay, so I am not going to write exactly like this, I am just rewriting slightly in a different manner, just a minute. So I am multiplying and dividing it so that delta 1 into u infinity is here and delta 1 is defined in this particular fashion, okay, and delta 2, so I am multiplying and dividing by u infinity square, and divide by u infinity square, this will be 0 to delta 1 minus u by u infinity into u by u infinity dy. Okay. So this is also another nice form that you find in many of the textbooks. Nevertheless, all the three, whether it is this form or this form, they are all the momentum integral equations or integral momentum equation. Okay, I personally prefer looking at this form. This is almost the final form, and this gives you a lot of information, because here this delta 1 which I have defined here, there is a particular name to it. This is also called the displacement thickness, and delta 2 here is called the momentum thickness. Okay, so and this is your okay. I hope you have a good understanding of what is displacement thickness and momentum thickness, okay, from your incompressible flows. I am not going to go into an explanation for that now. It is only, so these are not really measurable, okay. This is what you have to understand. Unlike the boundary layer thickness, which you can measure as a location, these are conceptual values which give you a sense. If you suppose replace the boundary layer with a potential flow profile, so how much the wall has to be pushed up, okay, so are displaced in order to satisfy continuity or satisfy conservation of momentum, okay. So that is this location. So these are all not measurable, okay. These are something which you are conceptualizing, and usually these are much smaller than your actual boundary layer thickness, okay. So this is your momentum integral equation. So you are writing this in terms of the momentum integral, your displacement integral, and so on. For the case of flat plate without the pressure gradient, the second term will be 0, so you do not have anything in terms of the displacement thickness. So for flat plate, your du infinity by dx is equal to 0, and this will lead to the form. You can write u infinity square d by dx 0 to delta okay. So this is the integral momentum equation for flat plate. Let me call this as number 1, okay. This is the one form that we will be using to substitute all our approximate profiles. Now same way we will derive the integral form of boundary layer energy equation, okay. We start from the conventional energy boundary layer equation, and then we integrate it out across the boundary layer thickness, and we arrive at a similar integral energy equation, okay. Okay, so we start with our standard energy equation. We do not assume any viscous dissipation term here for flat plate case. Without viscous dissipation, this is your equation at y equal to 0. It could be either wall temperature is fixed or your prescribed heat flux which is constant, and at y going to infinity, t is equal to t infinity at x equal to 0, also the same thing follows. So what we are simply doing is integrating again. Now when we are integrating now, we cannot integrate it till the boundary layer thickness, because now we have to integrate it till the characteristic thickness for the energy, which is the thermal boundary layer thickness. Okay, so we integrate it till delta T. Of course, we are not making any assumption whether delta T is greater than delta or less than delta. Whatever extent it may be, we are just integrating till the edge of the thermal boundary layer. And so we will try to eliminate V, so that we write everything in terms of U. So we will see that the second term can be integrated by parts. So this can be written as 0 to delta T okay. I can write this as d by dy of Vt, integrate between 0 and delta T, so that is nothing but V into T between the limit 0 and delta T, okay, minus integral 0 to delta T into T dV by dy, okay. On the other side you have alpha delta T by del y between the limit 0 and delta T, and at delta T dt by dy is 0, okay. It has to satisfy continuity in slope at the edge of the boundary layer. So therefore, so this will become minus alpha dt by dy at y equal to 0, okay. So this is coming because at x is equal to y going to infinity, t equal to t infinity, therefore dt by dy has to be 0, okay. So now this particular term again at y equal to 0, v is 0, so that this will be valid number only when you look at y equal to delta t. So where once again your t will become t infinity there, okay. So at delta t this will become t infinity, okay. So this is at delta t. Is that fine? So now what we can do is once again we can integrate this by parts. You can write this as 0 to delta t into d by dx of ut dy minus 0 to delta t du by dx dy, okay. So therefore you can combine this and this term right here. So you can take t common, this is du by dx plus dv by dy, which is nothing but the continuity equation, alright. Therefore I can write this as 0 to delta t d by dx of ut dy plus vt infinity minus I can take 0 to delta t common, du by dx plus dv by dy, this is equal to minus alpha dt by dy at y equal to 0. So and this also satisfies continuity, so this goes to, okay. And also from continuity you know that my v equal to minus 0 to, if I integrate from 0 to delta t the continuity equation, I can write my v velocity in terms of u velocity. So just the continuity I am integrating, okay. So I can substitute, and now I can eliminate v from this equation. So if I write this in terms of u velocities, this will be 0 to delta t, I can take d by dx out, d by dx ut dy minus I have t infinity into integral 0 to delta t du by dx minus alpha dt dy y equal to 0. Okay, so I just want to combine these two terms. I can write this as now d by dx, okay, 0 to delta t. I multiply by minus sign throughout. This will be t infinity minus t. So u is common for both. I can write this as u dy. This is equal to alpha dt by dy at y equal to 0. Okay, so this is my final form. This is the energy integral equation. Okay, so I can combine these two terms because t infinity is anyway constant. I can take this, I can write this as d by dx of t infinity u. So u is common in both the cases. I can combine this. Okay, so now we have both of them. So I am going to define my theta. In fact, I can write in terms of theta, but let me do it later. So just let me write down the energy equation, energy integral 0 to delta t infinity minus t u dy should be equal to alpha. Okay, so this is your equation number 2, which is your energy integral. Okay, so the first step is that we derived the integral form of momentum and energy, and we have put it in this particular pattern. And next, what we are going to do in the approximate solution, we are going to make an approximate assumption for the velocity and temperature as some polynomial. Okay, so it can be any order polynomial, and we have to see which boundary conditions that the profiles have to satisfy to calculate the coefficient of these polynomials. So this is the next step. So now let us take the case where we have a linear velocity profile. That is the most basic profile that you can start with. So for the laminar flow, let us assume a linear velocity profile. So I am just saying that my u would be something like a plus by. Okay, this is the linear form of the velocity profile that I am assuming. So in order to get the constants a and b, I have to satisfy boundary conditions. Okay, so you have to start with the most basic boundary conditions before we go to satisfying the more higher order boundary conditions. Okay, the most important boundary conditions start from the wall at y equal to 0, u equal to 0. Okay, and after this, what should be the second most important boundary condition? So once you have given at y equal to 0, you have to give something at y equal to delta. Okay, u equal to u infinity. These are the most basic boundary conditions which have to be satisfied. I cannot directly say du by dy at y equal to delta is 0 has to be satisfied. Then it does not tell what value it should reach at y equal to delta. Okay, it just only says that the slope is 0, that is it. So if you substitute, can you tell me what will be the profile that I get? So if you directly substitute this, y equal to 0, u equal to 0, your a will be 0, at y equal to delta u will become u infinity, therefore b will be u infinity by delta. Okay, so therefore your u will be equal to u infinity y by delta. So u by u infinity will be equal to y by delta. So this is my linear velocity profile. So if I plot this profile for a flat plate at any location, it will show only something like this, a very linear variation from 0 to u infinity. At y equal to 0 u will be 0 and varies linearly. At y equal to delta u will become u infinity. So this will be delta, something like a coed flow profile. Okay, so this is not actually the real profile, right? Your real profile is for satisfying a different relationship which we have seen from the Black-Scholes solution, and definitely the shape doesn't look like this. Okay, there is a slope, there is a curvature terms are all there, okay, which we are not accounting for in this particular. Okay, the slope is constant and there is no curvature. So therefore this may not be a very good profile, but still this is an approximation. Okay, so why we are approximating it is, once we may give this kind of an approximate profile, we can substitute for velocity in this momentum integral and we can directly calculate the boundary layer thickness. The expression for delta can be determined. So what I am going to do now is substitute this profile into 1. So if I substitute into 1, so that I will get u infinity square d by dx 0 to delta into 1 minus, so u by u infinity now will be y by delta into y by delta into dy. On the right hand side I have nu du by dy at y equal to 0. So du by dy now will be what? U infinity by delta, okay, from the linear profile. So therefore, so anyway that is a constant slope, it does not matter whether it is at y equal to 0 or, so this is just a linear profile, so the slope is constant, so this will be nu into u infinity by delta. Okay, so very simple profile and the equation also looks simple. Now I am going to introduce a non-dimensional variable eta which is equal to y by delta. Okay, do not confuse this with the similarity variable. Of course I am using the same variable here because coincidentally in the similarity solution also eta was the similarity variable which was related to y and delta exactly like this, but here I am just using eta to represent any non-dimensional variable. So if I do that, I can transform y in terms of the non-dimensional eta. This will become u infinity square d by dx. Now integral from 0 to delta will become 0 to 1 in terms of eta. Okay, so 1 minus eta into this will be dy by d eta into d eta. Okay, dy by d eta will be delta. So basically I can put this delta here into d eta. Okay, which will be equal to, on the right hand side, nu u infinity by delta. Okay, now this delta has to be with inside d by dx because delta is a function of your position along the flat plate. So if you do the integral, maybe you can take a couple of minutes and do it, but since we do not have time, I am just going to give you the final solution. So this will come out to be 1 by 6. Okay, so the integral 0 to 1 minus eta into eta d eta should come out as 1 by 6. Okay, so in that case this will become, I can cancel u infinity on both sides and this will be, delta will come to this side, so delta d delta by dx will be equal to 6 nu by u infinity. Okay, so now this is a very simple ODE which I can solve by separation of variables straight away. Okay, so this will be delta square will be equal to 12 mu by u infinity x plus some constant. Okay, this is the solution for delta. Of course we can find the constant by applying the boundary condition that at x is equal to 0, delta equal to 0, right. The boundary layer thickness is 0 at the leading edge of the plate and therefore your constant will be 0. Okay, so your expression for delta now reduces to the form delta is equal to square root of 12 nu x by u infinity, which is nothing but 3.47 square root of nu x by u infinity, or delta by x can be written as 3.47. I can divide by x on both sides, and this will be u infinity x by nu, which will be nothing but square root of Reynolds number. This will be square root of Reynolds number. Now you can compare this with the similarity solution from which we calculated the expression for delta. Do you recollect what is the expression there? That was 5. Okay, so how did we do that? We calculated for different values of eta f of 0, f prime of 0, and also at all other values of eta we have tabulated, and we found out the corresponding value of eta where your u by u infinity or your f prime was 0.99. Corresponding to f prime 0.99, we found that eta was equal to exactly 5, and that is nothing but the value of delta. Okay, so this is how we have got it approximately. The actual solution is delta by x is equal to 5 by square root of Rex. So since we are using an approximate profile, this is the variation, you know. So this is about 31% less than the exact solution. Okay, so there is an underestimation that we get by using the linear profile. And we can go ahead and calculate the wall shear stress local variation, which is nu du by dy at y equal to 0. Okay. So in this case du by dy at y equal to 0 is nothing but for the linear profile u infinity by delta. Okay, so this is nu u infinity by delta. So we have already got the expression for delta, which we will substitute here, and if you do that you will get 0.288 u infinity square root of by nu x. Okay, so now if you define non-dimensional local skin friction coefficient as tau l by rho infinity square, so this will come out as 0.576 by square root of Reynolds number. Okay, so and if you remember, the exact solution was giving 0.664. Okay, so this is about 13% less than exact solution. Okay, so if you also go ahead and integrate the local skin friction coefficient over the plate and calculate the average skin friction coefficient for the entire plate, that is your CFL is equal to 1 by L 0 to L CFX dx. Okay, so we will end up with the expression 1.152 by square root of REL. Okay, so finally the bottom line is this: you can get an approximate estimate of all these quantities like boundary layer thickness, your local shear stress, skin friction coefficient, everything using some approximate profiles, and this is much easier, as you can see, than doing a rigorous solution to the similarity equations. Okay, and in fact if you use a better profile, you will be amazed to find that the agreement will be even better. Okay, so just to give an example, if you go from a linear profile to a cubic profile, okay, which I will just show you and stop there. Okay, so if you assume a cubic velocity profile, u is equal to a plus by plus cy square plus dy cube. Okay. So now you have 1, 2, 3, 4 coefficients, and we have to satisfy therefore 4 boundary conditions. So what are the possible boundary conditions? Y equal to 0, u equal to 0, and at y equal to delta u infinity. So these are the important boundary conditions. And what is the next important boundary condition? At y equal to 0, rho u by dou y. So if you look at the momentum equation, okay, so u du by dx plus v du by dy is equal to nu d square u by dy square at the wall. Okay, both are 0. So therefore d square u by dy square has to be this is the next important. So in the order of importance I am writing it. Okay, and then finally what is the last boundary condition that you have to give? Cubic. In terms of the order of importance, okay, so these are most important, and then at y equal to 0 this is to be given, and then y equal to what? Delta okay. So these are the 4 important boundary conditions. So if I substitute these boundary conditions into the profile and you calculate all the coefficients, finally I will be able to arrive at an expression which is like this: u by u infinity will be 3 by 2 y by delta minus 1 by 2 y by delta the whole cube. Okay, so this is the cubic velocity profile that you will get. I am sure most of you have taken the heat transfer course have done this also in advanced heat and mass transfer in incompressible fluid flows also. Okay, so cubic profile is like the accurate profile that you can do. Okay, so once you get this, and if you substitute the same way that we did the linear profile into the momentum equation, so let us see what happens to the final expressions. The final expression for delta that comes out with the cubic profile will be 4.64, that is correct. Delta by x will be 4.64 by square root of Rex. So you can see a remarkable improvement. Okay, so this is like 7% less than the exact solution. And when you look at the skin friction coefficient, so this value comes out as 0.646 by square root of Rex. This is like almost there, 3% less. Okay, so this is 0.664, this is 0.646, almost there. So you can see that with a cubic profile you get a very good approximation, very accurate solutions, okay, rather than going for a very rigorous similarity solution. So nowadays I think many of the people they are not so interested in the similarity solution, because you have numerical techniques where you can directly solve the governing equations, okay, and or you can also resort to solutions like approximate methods with the integral equation, where you can make use of some approximate polynomials and also get the solution. So that's why these are more popular methods, okay, and which are also workable in a very short time. But you have to be cautious. That doesn't mean that if you keep increasing the polynomial, now this accuracy will become better and better. Okay, so for example, if you go from linear to quadratic and from quadratic to cubic, you will find that it doesn't progressively increase in terms of accuracy. Okay, in fact quadratic in fact spoils the solution a little bit. That's mainly because in the case of quadratic boundary conditions we give this boundary condition, and finally this boundary condition. We don't give this particular boundary condition. Okay, so because we have only up to here, we don't give up to this boundary condition. Because of that, you will find there is a degeneration in the accuracy, the quadratic case. Again with the cubic, it satisfies all the fundamental boundary conditions and the accuracy goes up. And if you use a fourth order polynomial, again you may have to give something like y equal to delta d square u by dy square equal to 0 basically, and they may not be very important, the error may not come down all the time. So that's okay. So in the animation for the temperature profile, the same way that we did thermal boundary layer thickness, and therefore these aspects in the next class. So quickly we will move familiar with the heat transfer course, so we are not going to spend much time. We will do this analysis for flows with pressure gradient, similarity flows. Is that dealt with in the other courses or no, where you have done similarity solution for adverse pressure gradient flows or pressure gradient flows? I am sure something must have been done in incompressible flows, the Thwaites method and Karman-Polhausen method. Okay, so maybe we will cover those aspects in the future next 4 or 5 lectures. Okay.